Let's start. Welcome everyone for today's DAA seminar, and it's a pleasure to have Dr. Raghunath Ghara as our speaker today. So I invite Shubhadeep Mukherjee to formally introduce the speaker before the talk starts. Please, Shubhadeep. Thanks.
Thank you, Saurabh. It's a great pleasure for us to have Dr. Raghunath Ghara with us today, talking about probing the intergalactic medium with hydrogen to interstellar radiation. He is currently a postdoctoral fellow at the Department of Natural and Life Sciences in the University of Israel, in the Open University of Israel. Previously, he did his PhD from NCRA in the year 2016, and then he has done a couple of postdocs in University of Stockholm and also in Israel University at Technion. So it's a great pleasure for us to have you today over here, and please take it away whenever you're ready. Thank you.
Okay, thanks for the kind introduction. So in this talk, I'll be basically talking about the medium between the galaxies and how we can probe that using hydrogen. Now, to introduce the topics, so here I'm basically showing the evolution history of our universe. And if you see at the very right of this figure, then you will see many, many galaxies, and the medium between these galaxies are mostly ionized, with at least the ionization fraction is very high. Neutral fraction should be less than 10 to the power minus 4 or so. And it is also very highly heated. So temperature must be like 10 to the power minus 4 Kelvin or so. Right. We have quite good understanding at this local universe, and also from the observation of cosmic microwave background, we also have quite good understanding at the very early epoch of our universe, when this radiation, CMB radiation formed and the universe become neutral. Now, with the formation of CMB, the universe will become neutral, and so ionization fraction was almost zero, and it was like at that point it was hot, but temperature drops as the universe was expanding. So this dark edges part, which is roughly, let's say, exists between let's say 1,000 to 30 or 40 in terms of redshift. The universe was neutral, the temperature was dropping at around redshift 30, the universe was quite cold. Right? At that point, the first stars, the population 3 stars, they start to form. And also the X-ray binaries start to form, and basically the X-rays, which can penetrate longer distance in the neutral medium, they start to heat up the medium. So that phase we call as cosmic dawn, where mostly the heating of the universe was done. So from this cold state of the universe, the temperature, average temperature, they increase. At the same time, at a later phase, let's say at around 20 or so, first galaxies start to form, and the UV radiation from these galaxies, they start to ionize the medium. Of course, the ionization was happening before also, but the fraction wise it was quite small. But more and more sources formed, and this ionization process that become very efficient. And this individual ionized region, they start to overlap and reionize the universe, highly reionize the universe. Sometimes with when the age of the universe was 1 billion years, or in terms of redshift, it was like 6. So this phase where the majority of this ionization was happening is called reionization. So as you see, the latter phase of our universe, which remains highly ionized in this post-reionization, this is more or less not that much things to investigate in terms of intergalactic medium states, the thermal and ionization state. But the phase change, what is occurring during the cosmic dawn and epoch of reionization, this is like in terms of the thermal state and ionization state, is very interesting, and is majorly they can also change the formation of star formation in the latter stage. So has quite high impact. Now, for this, I will be using this hydrogen 21 centimeter signal. Now, this signal is basically originated from hyperfine transition of hydrogen. Wherever there is a hydrogen atom, this radiation line emission happens, and with a frequency, rest frequency of 1420 megahertz or a wavelength of 21 centimeter. So that's why this probe is called 21 centimeter probe. And if there is a some amount of hydrogen is somewhere, then the amount of radiation emitted by this part of this hydrogen or the intensity, they depends on the relative population between these two hyperfine states, which can be characterized by a temperature called the spin temperature. Now, this spin temperature or the relative population of the hydrogen in these two states depends on various mechanisms. One is the scattering with the CMB photons with the hydrogen atoms. Hydrogen atoms, they can collide and they can also change the relative population. Also, there is one mechanism called field effect, where lamina of a photon emitted from the sources, the galaxies or stars, they are basically absorbed by neutral hydrogen, and they can reshuffle or change the population in between these hyperfine states, while they basically the lamina of a photon, they are very easily absorbed and also re-emitted at the same time. But in these two processes, they can change the relative population, and thus they can influence the spin temperature of the population. So this probe I am going to use. Why hydrogen? Because this is the most abundant element in the universe. It is like in the several megaparsecs of scale, we can observe it, and so we can probe basically the large scale structure as well. So with this 21 centimeter probe, is not only we can probe the properties of the intergalactic medium, but we can probe many things. For example, if we can probe the dark edges, at least let's say from redshift 150 to 30, this part we can probe with some space-based radio telescope, which doesn't exist at the point, but later it will exist. So with that, we can probe how the fluctuations actually evolve with time, or the density power spectrum, for example. So we have quite good understanding how the power spectrum looks like at this time when the CME form, but we don't have any information how the power spectrum evolves in between in this intermediate phase. We have some idea about the local power spectrum with the observation of hydrogen from which resides on the galaxies, but in this intermediate phase, which is very uncertain. So if as this is a line emission, so it's basically it is redshifted, and frequency wise, it will be different at different redshift, right? So if, for example, if we are talking about observing a 1420 megahertz observation, that means the hydrogen which we are probing is at local universe, at redshift 0. If we want to probe a higher redshift universe, then we have to go to a lower frequency. So here, if we go to a lower frequency observation, then we can probe different parts of the dark edges, and thus we can probe how dark matter power spectrum actually evolves. And in this cosmic dawn era, the heating is happening, so we can probe how this heating and different morphologies of the heated regions they are evolving. Also, we can probe the types of sources which are basically driving this heating process. This is the phase where the seeds of the supermassive black holes reside, so we can also probe those. We can this phase in the cosmic dawn where the lamina alpha radiation background grows and becomes saturated, so we can probe that too. And we can probe the first stars which have formed in the universe. Those are these population 3 stars. So many very important physical process happening in this cosmic dawn era. And in the epoch of radiation era, it is also of very great importance because we can probe the first galaxy. JWST is now detecting some of those. And with each one, we can probe those. I will come to just a few minutes. I will come how we can probe those. And here, like the ionization process is happening. The bubbles are growing with time. So we can probe like how the morphology of these different regions and their impacts on the star formations. Because ionized region, those will be heated and they will suppress the star formation. Right. So all these things we can probe during the epoch of ionization. So both the epochs. So I will basically concentrate on the cosmic dawn and epoch of ionization part, because as I'm talking about the intergalactic medium, so these are the two phases where mostly very interesting physical processes are happening in terms of intergalactic medium. Now, let's first talk about how we can actually probe or observe the H120 centimeter signal. The idea is basically very simple. If at some part of the sky, if there is neutral hydrogen, which is emitting this 21 centimeter signal, which is redshifting to us. So it emits at a frequency of 40-20 megahertz. But if this cloud is at redshift Z or redshift, then we will be observing at that particular radiation at a lower frequency, which is given by this frequency, right? So let's say we observe at 100 megahertz with our radio telescopes. Whatever is emitted in the line of sight is basically measured. So many things will be actually measured in addition to the H1 signal, which is emitted from this one. One obvious thing which will be added is the CMB part. But we have a good understanding of what the contribution will be, and we can subtract the CMB part. And as it is in the radio frequency, so we can convert the entire thing into brightness temperature. And theoretically, so this is one expression to which basically tells what the intensity will be. So this is the differential brightness temperature. So we basically measure this signal and subtract the CMB part and convert that to brightness temperature, and this is the quantity. So this particular things depends on neutral fraction, this XH1, spin temperature, CMB temperature, and cosmological parameters. This particular part depends on this relative velocity of gas. So that will basically sit in terms of redshift space. So mostly the astrophysical imprints are in these two quantities, in terms of these two quantities, which is the neutral fraction and spin temperature. How? So first of all, the UV photons, which is emitted from the stars and galaxies, they will change the neutral fraction. And just around the sources, medium will be highly ionized. So it will be basically neutral fraction will be 0. So the differential brightness temperature will be 0. While there is a neutral region, then there will be signal, but in terms of brightness temperature, that can be negative or positive. So that depends on the strength or the value of spin temperature. Now, as I said, spin temperature, that depends on various mechanisms, right? So that can be a value which is smaller than the CMB temperature, or if the heating is happened quite significantly by the X-ray sources, then the CMB temperature, the temperature will be lower than the spin temperature. If the spin temperature is greater than the CMB temperature, then it will be basically brightness temperature. Differential brightness temperature will be positive value. That we term as emission signal. In other case, where the spin temperature is smaller than the CMB temperature, that we term as absorption signal. Right. So let's now see a view of the realization and cosmic dawn in terms of this 21 centimeter brightness temperature. So for that, I am using my code, this Grizzly, which use 1D radio transfer and outputs from inboard simulations to simulate the signal in 3D box. And it's basically like I take a different spectrum, like galaxy type spectrum or mini quasars or high mass X-ray type spectrum. And I do 1D radio transfer around the sources. So this particular figure here, which I'm talking about, the panel, shows the ionization fraction as a function of radial distance from the source. So source is sitting somewhere here. And as you can see that some age, for this, I'm assuming like 30 mega year of age, the profile of the ionization fraction looks like this. So roughly like at this one, a typical, probably this is a source of stellar mass of 10 to the power 8 or so. As you see that tens of co-moving megaparsec is highly ionized at redshift 10 or so. And after that ionization fraction, this decays, but it is not very sharp. It decays smoothly. So what happened? This part, actually, X-rays are important. X-rays, they have penetrated and has partially ionized the region. So there will be a very sharp cut in terms of neutral fraction or ionization fraction. But after that, the front will be with partial ionization, and that will be due to X-rays. If X-rays doesn't exist, then this profile will be very sharp. And this second panel, I am showing the gas temperature, while you see that while this region is highly ionized, the temperature is of the order of 24 Kelvin. And after that, it decays, and it's this particular region where it is kind of neutral, but with a temperature larger than the CMB temperature. Now, CMB temperature is this. So this will be in absorption region, and this particular phase where the gas temperature is lower or the CMB temperature is lower than the T gamma, this will be absorption signal. So around the source, as you can see, if there is X-ray source, then there will be a small ionized region, and after that there will be an emission region, and after that there will be an absorption region. So in this panel, I'm showing one light cone. Now redshift increase in the rightward direction. So my simulation starts from the right at redshift 20, where there is only few sources in the universe formed. So Lyman-alpha background is not that strong. So mostly like it is the CMB scattering which is determining the spin temperature, which is trying to equalize the spin temperature to the CMB temperature. The signal is mostly very weak, 0, it starts very weak. But over time, the Lyman-alpha fluctuations and Lyman-alpha, the background, that increase. And that to say, it become most of the region, the Waddesdon field effect, that become important. And the CMB, the spin temperature for most of the region became smaller than the T gamma or the CMB temperature. At that phase is basically the absorption signal which dominates the universe. But over time, X-ray source formed, and you see that these small red regions, which are basically the emission regions. So these are the heated regions, and heating happened due to the X-rays emitted from the sources. Okay. Over time, more and more X-ray sources form, and these X-ray regions, the emission regions, they become bigger, and they basically merge together, overlap, and complete the heating. So in this model, like which I am showing, heating is very significant by redshift 12. Okay. After that is basically the red part in this reionization is emission region. So universe, the neutral part of the universe is also heated. And after that is the black regions which grows over time. So black regions are ionized regions. Yeah, okay. So ionization is driven by the UV photons or the galaxies, and they also follow the similar trend of the emission regions. They also grow over time and merge together and complete the reionization. In this model, it is completed by redshift 6 or so. So this is more or less the view of cosmic dawn and epoch of reionization in terms of 21 centimeter, right? So as I said, the observationally, the idea is very simple, and many telescopes actually are now trying to measure the signal from epoch of reionization and cosmic dawn. And some of the experiments which are going on currently is like LOFAR, ARCFAR, NENUFAR, MWA, HERA. And these are interferometer based observations. SK will come very soon. These have, yes.
Excuse me, I think Shubhadev has a question.
Yes, so feel free to interrupt me anytime. So I'm not actually looking at this one. So, but it should be very informal. So whatever, if you have any questions, just interrupt me. I'll be happy to answer.
Okay,
It's
good.
okay, no, but raise the hand, I will stop her.
Okay, that's
I'm keeping an eye.
Should I go ahead?
yes, yes.
Okay, thank you. Can you please put the previous slide?
Yes.
So that the profile that you are showing, how will that differ depending upon the initial emissions from the galaxies or the quasar or the individual source properties around which you are seeing the signal?
Right. So these profiles are pretty much source dependent. As I said, like for example, here I'm showing two types of spectrum. One is the galaxy spectrum, and you can see there is almost no photon which has energy larger than 50 electron volt or so. So no X-rays in the galaxy model. So ionization wise, it is the UV part. If you integrate photons up to let's say from energy 13.6 to let's say 50. So these are the photons which are basically doing the ionization part. If you take a very bright ionizing UV emitting source, okay, so that means your ionized region around the source, which is this, which is like 1 co-moving megaparsec in this one, that will be bigger. Because it's a more ionization photon, so more ionization will happen around the source and the ionized region will be bigger. X-ray wise, now here the second source, the dotted curve, the blue one, this particular SCD contains X-rays up to energy of 10 kilo electron volt or so. Now this, of course, like if you increase the amount of X-rays emitted from the source, for example, like if instead of high mass X-ray binaries, if you take quasars, which is very bright in both in UV and X-rays, so there you will find this transition will be similar, but the amount of ionized regions and heated regions, those will differ. So that the amount of ionized regions, emission region, and absorption region around the source, those are dependent on the different properties of UV emissions, X-rays, and Lyman photons. So these are the three photons from the sources which are important, and the amount of these photons which are emitted from the sources that determine the amount in terms of volume of these three types of regions around the source.
Okay, great. Thank you.
Right. So I was talking about the observations. So these are interferometer based observations, and these are trying to probe the fluctuations. So as these are interferometer, they cannot measure the mean of the signal in terms of different redshifts, but they can produce fluctuations at different scales. For example, here we are showing how the fluctuations in terms of the power spectrum of this brightness temperature should look like at a scale of 0.1 megaparsec inverse. And these are the three peaks which is mostly theoretically understood. Where the first peak is due to Lyman fluctuations, second peak is due to X-ray fluctuations, heating fluctuations, and the third peak is due to ionization fluctuations. And this is the similar figure which I just showed previously. And these experiments are basically trying to detect those. So this is like a one indirect way to detect. And as you can realize that all this amplitude and the features in the power spectrum, those are dependent on the Lyman emission, X-ray emissions, and UV emissions. So those are very much connected to the source properties. Yes, Subhadeep.
Yes.
Do you have a question?
No, I didn't say anything.
Sorry. I see your breath. So there is a separate types of observation going on which use single dish radio observations, and that can probe the evolution of mean brightness temperature with time or redshift. And few examples are like Bighorns, AJS, LEDA, and SARAS. SARAS is India-based observations. And both are basically trying to measure, but as I said, it's basically an observation at a frequency, let's say 100 megahertz or so. Whatever is emitted in my path, so at that frequency from my universe, that will be basically we will basically measure that one. So for example, let's say this is my signal, which is very weak, of a few tens of megakelvin, millikelvin order. But this is like, let's say, is emitted from redshift 6 or 7. But while it is propagating and appearing to a frequency of 120 megahertz, there are other sources which are redshifting and appearing to the same frequency. And these sources are extragalactic foregrounds from our own galaxies, RFIs, etc., etc. So everything is add up, and what we measure is not the signal at all. It's basically the foreground dominated signal. While the foreground dominated signals are several orders of magnitude larger compared to the 21 centimeter signal part. So that make it very challenging to separate out the very weak signal from the total measurement. However, the good part is that whatever is added besides the signal has a very frequency smooth spectrum. So using that feature, we can actually separate out the foreground part, and we can recover the 21 centimeter signal part. So this is the theoretical understanding, and observation groups are basically using this property to do their to apply their methods to separate out the 21 centimeters signal part. In terms of observation, there are other problems as well, and that problems comes from the instrument. So I'll not go into details of those because those are there, and the observation teams, they know their instrument very well, and they do the calibration and take care of the other problems if there are like deflections, sensitivity issues, etc., to in their data process to separate out the signal. So far, there is no, unfortunately, there is no detection of the signal. So it is slowly approaching to the detection, but it's not at the point, it hasn't reached that level. So far, whatever we have are upper limits on the fluctuations as well as the mean brightness temperature. And I'll be talking about one of the upper limits, which is from LOFAR. And as I also belong to this team, so I'll be talking about this observation and how we can use this observation to probe the intergalactic medium states. So LOFAR in 2020 produced this upper limit, which is in yellow. So whatever they measure is in this solid blue. Okay. So this is using 140 observations of LOFAR high-band antennas, and this probes receive 9.1. So after that, they subtract out the foreground part, they do the calibration, and they reach to this limit, which is basically that should be the thermal noise dominated limit. It's basically, it should be equal to the thermal noise of the instrument because it is the upper limit. That means the fluctuation level, it's in terms of the dimensionless power spectrum of the brightness temperature, which the upper limits mean that the signal fluctuation that should be somewhere below this. It cannot be above this limit, but still this is a very weak limit, but still we can use this limit to actually probe or rule out some of the IGM models, which I will be talking about. Now, so far, we have different observations from different radio telescopes of on the UR and cosmic dawn signal fluctuations. And this is a summary of those observations. The best upper limits are from Hera, still like an order or order 2, large compared to the what we expect theoretically the signal to be. But it is approaching. It means like, for example, LOFAR is also similar. If LOFAR add like at least 10 times more observation hours, then they should reach to this level. So it is like only time. So and the effort which need to give to the data analysis to reach to the signal level by which we expect. Right. So, but as you can see that this is upper limit, or even if it is measurement, this is only a line or few at different rates, but this is not telling the details of what we are looking for. It is not telling the information about the sources, or it is not telling about the information about the IGM. So here I will be mostly talking about the IGM. So, but you can use the same framework to constrain the source as well. So I did the LOFA interpretation paper, and for that I use this previously what I told about the Grizzly, that framework, that code, into a Bayesian framework to infer the information about the sources and the states of intergalactic medium at radius 9.1, which is the observational redshift at that point. Right. So in this framework, we basically use different source parameter, which is the ionization efficiency from the of the source, the minimum mass of UV photon emitting halo, and minimum mass of X-ray emitting halos, and X-ray efficiencies, and the spectral index of X-ray spectrum. So these are few parameters which we used into Grizzly code, and we ran many models. And that produced basically the expected path spectrum at radius 9.1, and we compare with the observable. So that's how, if you do it in Bayesian analysis, then you can put constant on the source parameter, which are this set. But at that point, I was asking this question: is this actually very reliable? Because the constant which we will put by using this framework, this is the model which we are using. If I change the model a little bit or include more sophisticated physics, then my constant on the source parameter, they can vary. So how robust is the constant on the source parameter? That was a concern at that point. So then I came up with the alternative idea. So this the concern about the constant on the source parameter will be always, it will be dependent on the source model, or the 21 centimeter signal simulating model, which we use. But it will be independent. If you talk about the intergalactic medium property, this will be independent of the model, because it's the morphology of the ionized regions or the heated region which create these fluctuations. So if you take a like inside out types of model, it's like the distribution of the ionized regions that will basically give the level of fluctuations. So few quantities from the intergalactic medium, like ionization fraction, heated fraction, gas temperature, and the size distribution of the heated regions, those should be sufficient to basically tell the level of fluctuations. However, at this point, we don't have a forward modeling which gives the power spectrum or the mean brightness temperature from the IGM quantities. We have this model which gives the observable, or here the power spectrum, for a set of source parameters. But for a set of ionization, for a set of IGM quantities, we cannot predict the power spectrum. So this model doesn't exist at this point. So what we did, we actually did this forward modeling from the source parameters to compare with the observables. But at the same point, we derived the IGM quantities, and we derived constants on these quantities. So just to see how we can use this this model to constant on the source parameter as well as the IGM properties, is that we ran many thousands of models, and this is the red is the upper limits, and we see only a few, so tiny fraction of our model is actually is above the upper limit. So these are the models. For example, the thick dashed curve. This is one model which is ruled out because this lie, at least at the very large scale, it lie above the upper limit. But at the point, you can notice that most of the models remains valid. So there is no point for going to constant on the source properties of the existing model. So what we did is that we did the statistics over excluded model, or the statistics over this set of models. So in terms of source properties, here, for example, the axis is the beta, the ionization efficiency, and mean. the minimum mass of halo, which emits the UV radiation. And this is the part which is basically ruled out, right? That means my ionization efficiency that need to be very high. At the same point, M mean have to be very large. That means the sources which emits the UV photon, that also need to be very small in number. So that means my reionization picture have to be very patchy. That is run by few sources, but very bright sources. Physically, this means like this. In terms of ionization properties, you see that the part of XH1, XH2, which is around 50%, is kind of ruled out. And in terms of the size distribution, bubble size distribution, which is if you use a mean free path type of technique, then the size distribution of the ionization regions looks like this, and you can characterize the size distribution by these two parameters, like while the peak is happening and the full width maxima of the distribution. And you can also put constants over this. So this is not from the Bayesian analysis. This is just from plotting these models in panels. But if you do the analysis in Bayesian wise and also include the spin temporal fluctuation, earlier it was it didn't do for the spin temporal fluctuation. It was only for the cold intergalactic medium models. Fluctuations was due to ionization fluctuations. But if you include everything, then we see that there is basically these two types of models which are ruled out. Mostly other remain valid. And to simplify, the constants is basically one set of models which are dominated by ionization fluctuations. Here, these yellow regions are ionized regions, while these green regions are cold region but neutral region. Reionization is very patchy. And on the other hand, the second types of models, and here there is almost no ionization happens, but the fluctuations is driven by spin temporal fluctuations. The yellow regions here are emission regions, and the green regions, these are absorption regions. So these two sets of models are ruled out by the weak upper limits from so far. Yes, Subodh.
Hi, yeah. Can you please go back to the previous slide? I have a question there. So these are constraints, and the R heat peak is the peak position of the bubble distribution. Is that correct?
Yes.
So yeah. So I was trying to understand that why is there a constraint in the lower side of the bubble distribution? Like because I can, if the bubbles are very large, fluctuations will be large. I can, and I don't see that in the upper limit, so I can put a constraint. But why I see a cutoff in the lower end?
It is not always that true. First of all, let's say you take only ionization fluctuations type figure. If the bubbles are very large, that doesn't mean that your fluctuation level have to be very large. Because if bubbles are very large, that can also mean that your universe is going towards highly ionization states. At that point, your fluctuations, because it is this type of feature, this particular part, it is due to the how much neutral hydrogen is in your part of sky. That also matter. In this part, your ionized regions are very big, but the part which contains neutral hydrogen, that is very small. So your overall like signal strength, that will be small. So it is not like that if you are taking a higher value of this RP, that is necessarily, that means that your fluctuation will have to be very high.
No, but what I'm trying to understand is if I go to the smaller values of bubble sizes, over there, do I still expect the fluctuations to be large because of some other parameters it is constraining? I understand the higher part. I don't have question there. I have question below R of 1.
So this part you can understand that
yes, that's right.
This part, that what I explained.
Exactly. I am
and
talking about that
part
end.
also. So this part also, like if your bubbles are very small, that means it is not giving the fluctuation or high fluctuations level at the scale which you are interested in. So if you're, it's basically like this Bessel type of function, if it is a spherical thing.
Okay, so you are
Right.
saying that because you do not see any fluctuations at all at any scales, that
So
tries to put some limit.
You see, the observation is at some scales, and this
Yeah,
is
yeah.
like tens of and hundreds of megaparsec scales.
Mhm.
Your fluctuations need to be high at the scale,
That's
especially at the large scales, and that is associated with a characteristic scale of the bubbles,
Mhm.
for which the fluctuations at the large scale, which LOFAR probes, is the maximum. If
Okay.
it is very small bubbles, then fluctuations are not at that large scale are not that much.
Yeah, so it should be lower. So I
Yes.
not be able to distinguish much.
So that's why like it is low probability there.
Okay,
If
maybe,
you are
but you have a
taking-
prior at that end, I guess, right? The prior's end over there, maybe.
Yeah, of course, like there is a prior, but
Yeah.
as you see that this is like with the Python, this MCMC, EMC, this
EMC.
one. It is somewhat different than the Cosmo EMC thing. The Cosmo
Yeah,
EMC,
yeah,
for example,
sure.
this has a like if you give a prior, then it automatically will reduce your this curve to the edge. But
Here it is
Python
doesn't.
one
Okay.
doesn't do that.
Great, great. Okay, thanks. That's what I was asking. Okay.
Right. So another lower upper limit is on the way, which should appear somewhat like early next year or so. And we checked that for that, there is quite a significant improvement at ratio 9, and the amount of model which we can rule out, they will increase significantly, which is, so previously it was a solid one, and the next one will be this dashed one, which is like a saying that at some point, if we add more observation hours, we can flip the problem. So now we are doing the statistics over excluded model. Then we can go and do the statistics over existing model, and that will be very interesting. But still, we have to wait for let's say few years to reach that level to do that statistics. Now, whatever I told, that is dependent on this framework, which use source model and use the IgM parameters as derived parameters, right? But this is very confusing in the sense, like I was talking that IgM parameters are the more fundamental parameters to probe. But at the same point, I'm telling that there is no theory that exists and that connect to the IgM parameters to the observable, which in this case is the fluctuations on the 21 centimeter power spectrums. So we are trying to develop that framework, and it is not easy. First of all, like the set of parameters for IgM, which I talked about, this is the entire set which we need or not. That we are not sure at the point. But we can use few features of the power spectrums. For example, in the left panel, I'm showing power spectrum of the binary temperature at different stages of cosmic dawn and stages of reionization. So this is a simplified model where we actually ignore the spin temperature fluctuations. So we are trying to develop a model of epoch of reionization where the model will be working on the IgM parameters, and that will give the power spectrum, something like that. So it is still in the progress, and so the model is based on the features which we see on the power spectrum at different states, and we can characterize or constant at few parameters, like where the peak of the which redshift the peak of the power spectrum is happening, and where the 50% ionization is happening, something like that. And we can actually put quite good constant on the ionization history, or here the evolution of neutral fraction. So we can put quite robust constant on that. So this is one thing, like a step towards the model which connects the IgM parameters to the observables of 21 centimeter signal. But this is still in progress, and I will be talking probably in the next talk. I will be talking more about this. But as this is in progress, I will not talk much about this one. While I talked about LOFAR, let's also talk about the SK, because this particular experiment will be very interesting because this will produce image cubes. And with the image cubes, there is plenty of things which we can do. First of all, like should be very easily detectable. And for example, with 200 hours of observations, with 5 sigma level of detection of very high rates, like 15 and rate of 15 high rate source positions, we can identify, right? And also the morphologies of the signal, that will be very interesting to see. And with these images, SK images, there are plenty of science we can do. For example, like the evolution of ionization fraction and the morphology of the ionized regions. We can use the image cubes from SK directly, the noise dominated image cubes. And we can use sophisticated algorithms like segmentations and then stitching to identify the ionized regions, right? So from the 21 centimeter signal image, we can make ionized region images. So that will be like directly say where the possible sources are sitting and the morphology of these ionized regions at the epoch of ionization. Same is also applicable for the cosmic dawn, but that part we will be basically probing the emission region instead of the ionized regions. We can also use morphological descriptors, the Euler statistics, etc., to characterize the shape of these ionized regions or emission regions. At the same point, as we can use like a match filtering type of technique, which not only increase the detectability of the signal, but also do help us to generate a size distribution of the emission regions and absorption regions. And one thing you can imagine that whatever statistic and the properties which I am talking about till now were based on the observation of this spherically average power spectrum of 0.10 centimeter signal. One drawback with these statistics is that it doesn't take into account the non-Gaussianity. So a huge chunk of information is actually lost. If we go to a higher order statistics like bispectrum, then the constant on the IGM parameter as well as the source parameter, that will be a huge improve. And we are doing some study to study like the detectability in terms of how many more hours will be needed and things like that. The match filtering is also one of such statistics, and the multi-frequency angular power spectrum, which is also one alternative statistics, which contains much more information compared to the power spectrum. So all these statistics will be very interesting in terms of the SK, because SK has this high sensitivity. So with other telescope, it is, for example, for going to bispectrum, is probably is not feasible. But with the SK, it's definitely these types of statistics will be useful to infer more information about the interactive medium as well as the sources. Right. With this, I will summarize. So I basically try to convince you that the 20 centimeter probe is very promising to probe the first billion years of our universe. And whatever constants we are having from the observations from the interferometers, radio interferometers, and single disk observations are very much useful to consider the sources as well as the interactive medium properties. Today's talk was focused on the interactive medium properties, but as you see that this is only the beginning. The upper limits are still very weak, but still SCAN ruled out several reionization and cosmic dawn scenarios, which are interesting. More upper limits are on the way, stronger upper limits, which will be useful to roll out more models, and at some points we will be able to flip the statistics to existing model, and that will be very interesting. But still, we have to wait a few years. So with this, I will stop, and if you have any questions, then I will be happy to answer.
Let's thank Raghunath on behalf of everyone, and thank you. Any questions? I see Shubhadev has raised hand. Shubhadev, go ahead.
Thank you. Hi, Raghu. Just one question about the bispectrum part. This is quite interesting. So, typically, at what scales do you expect this bispectrum to get important in the 21 centimeter signal? Like in what Fourier modes?
So this is still in the large scales. For example, like bispectrum, particularly, this is a bit complex statistics because now you are doing statistics with 3 Fourier modes, and there are like many possibilities of configuration which you can study. So first question is, what are the configuration with these 3 modes like K1, K2, and K3, which are interesting to study? So far, it has been shown that squeeze limit bispectrum, which is very much like going towards the power spectrum, those are content with information more than the power spectrum, but are content with information which are very powerful. Another types of configuration, which is equilateral type configuration, which also people use very frequently, also contains more information. But all this configuration, they are basically probing the large scale, because whenever you go to small scale, your noise there will be very high. For example, it's like similar, like the upper limits which I showed, for example, here. You see that the level of this upper limit, this is very increasing at small scale. So probing small scale with 21 centimeter signal, that need very high sensitivity. So with like existing telescope, none of them are like targeting to probe small scales. They know that small scales will be at least like above 0.5 or so. That will be completely like noise dominated. Only whatever information we can get is from the large scale part, which is, let's say, K value of below 0.5 or so. And for SKA, it will be up to similar scales in K, or it will be going slightly deeper? For SKA, I mean, the trend will be similar. Sure. It will be even easy to detect at the largest scales. Okay. But yes, for SKA, people talk about going to small scale. So it will be easier detecting the signal at large scale. So why not go to the small scale and use that information? That's right. Yeah. Right. So yeah, people for that with SKA. Nice. Thank you. Are there other questions?
I don't see any other hands raised. Other questions?
Okay, no problem. Like if you have any doubts or if you have any questions which come up later, then you can contact me. I'll be available. So we'll be happy to like interact with you in person. So no problem.
Great. So if no questions at this point, let's thank Raghunath again. Thank you.
Thank you. Thank you for the invitation.
Thank you. The meeting now.
Yeah. Okay.
Bye.
Bye.